Now that we have safely crossed the treacherous normalizing flow, we'll have a stroll through the unrolling hills of time toward our destination at Backpop Bay. In this video, we'll discuss some algorithms for inference and uncertainty propagation in time series and dynamical systems. We're looking at time series models where the state at time t+1 is a function of the state at time t and some additive Gaussian noise. We also assume that the initial state x0 is Gaussian distributed. The function f is called a transition function or the dynamics function. In many applications, we're interested in computing an expected utility where the expectation is taken with respect to state trajectories tau. A trajectory is a sequence of states from the initial state at time 0 to a final state at time t. For example, in reinforcement learning and optimal control, the utility is the long-term reward or cost. But these kinds of utilities also appear in other areas, for example in logistics, when we forecast demand and associated costs, or when doing weather forecasting, which can be used for assessing the risk level of flooding. The main challenge in all of these scenarios is to do long-term predictions, which requires uncertainty propagation. Uncertainty could creep in through uncertain initial states, noise in the system, or if we learn F, uncertainty about some model parameters. We're looking at two approaches for long-term predictions. First, we'll discuss deterministic inference approaches, where we iteratively compute the state marginals p of x1 to p of x capital T, and then compute expected utilities at every time step by computing this integral. By summing them up, we get to the expected long-term utility. A second approach we'll discuss is stochastic inference via trajectory sampling. Here we generate sample trajectories tau s and use Monte Carlo integration to get the expected long-term utility we are interested in. Now let's first look at deterministic approximate inference. Here we iteratively compute the state distribution of the next state at time t+1, which is the integral of the next state distribution given the current state at time t, which is shown in orange, times the state distribution at the current state, and we integrate out the current state. In our case, we assume additive Gaussian noise in the dynamics so that the orange conditional distribution is Gaussian with mean f of xt and covariance matrix Q. Unfortunately, if f is nonlinear, this integral cannot be solved analytically, and we have to find some approximations. A common approach is to iteratively approximate the state distributions p of xt using a Gaussian with mean mu t and covariance matrix sigma t. This means, as an illustration, that at every time step we push the Gaussian distribution of the current state through the transition function and approximate the distribution of the state at the next time step with a Gaussian. We repeat this procedure until we reach the end of the trajectory. This is also illustrated here on the right-hand side. So we start off with a Gaussian state distribution at time 0 and then push it iteratively through the dynamics function and approximate at every time step using a Gaussian until we reach time step capital T at the end. The question is how to determine the mean and the covariance matrix. There are some classic approximations that have been around for decades and which are heavily used in engineering. For example, we can linearize the transition function locally and compute the mean and covariance of the next state distribution in closed form. This kind of approximation is at the heart of the extended Kalman filter. An alternative approach is to use the uncentered transformation. Instead of approximating the nonlinear function f, it approximates the input distribution using a small number of deterministically chosen points, and then determines the mean and covariance as a weighted maximum likelihood estimate. The uncentered transformation is the core approximation that is used in the uncentered Kalman filter. A third option that is sometimes possible is to compute the mean and the covariance of the next state distribution in closed form, and then approximate it using a Gaussian that has the correct mean and the correct covariance. We would ignore all other higher order moments of the true distribution. This is called moment matching and is used in the assumed density filter. So let's recap. We want to compute the predictive distribution of the state at time t+1. For this we have to solve this integral, and we make the assumption that the state at time t is Gaussian distributed. We'll discuss two approaches in more detail. First, we approximate the function inside the integral by linearizing it, which allows us to compute the mean and covariance of xt plus 1 for this linearized function. Then, as an alternative approach to computing the integral, we approximate the state distribution p of xt and use the uncentered transformation to compute an approximation to the mean and covariance of the distribution of the state at time t plus 1. Let's get started with linearization. The key idea is to locally linearize f around the mean of p of x and then compute the predictive distribution for the linearized function in closed form. Because p of xt is assumed Gaussian, the distribution of xt plus 1 for this linearized function is also Gaussian. In other words, we perform a first-order Taylor series expansion of f around mu t, and that requires us to compute the Jacobian of f evaluated at mu t. Once we have this linearized function, we exploit that we can push the Gaussian input distribution through the linearized function analytically. The reason for this is that an affine transformation of a Gaussian remains Gaussian. And here's how it works. First, we compute the gradient of the function with respect to x and evaluate it at the mean of the input distribution. We then get this linearized approximation, which is also shown here on the right-hand side as this purple line. From here, we can use the rules for affine transformations of Gaussian random variables to get this approximate distribution of the next state. In this final step, we also add the noise covariance matrix. Linearization is conceptually pretty straightforward, but it does require a differentiable transition function. An issue in practice is that it often tends to underestimate the true covariance matrix, which can lead to overconfident predictions. Especially in downstream applications, this can be a problem if risks cannot be properly taken into account. Compute-wise, this approach scales cubically with the dimension of the state. Although this approach is so simple, it's used all over the place in engineering. For example, it's in GPS and helped out in multiple Apollo missions. The second deterministic approximate inference approach we discussed today is the uncentered transformation. The key idea here is that instead of linearizing the transition function, we represent the input distribution using a deterministically chosen set of so-called sigma points. We then map these sigma points through the function and use them to compute a weighted average of the mean and covariance of the predictive distribution. Here's how this works in some more detail. Assume our state lives in a d-dimensional space. We then choose 2d plus 1 sigma points using this expression here. Here mu t is the mean of the input distribution, and square root sigma is a square root of the covariance matrix. Alpha is a scaling factor that spreads out the sigma points symmetrically around the mean. Now that we have the sigma points, we can now map them through the original function f and compute the mean and covariance of the predictive distribution as weighted averages. If the weights are 1 over 2d plus 1, we get the maximum likelihood estimates. But there are more sophisticated ways to set these weights. Let's have a look at some of the properties of the uncentered transformation. First, I want to mention that this is not a Monte Carlo method. The sigma points are deterministically chosen. There's no source of randomness. A good thing here is that we don't need to compute the Jacobians. That also means that the transition function can be non-differentiable. Also, the input distribution doesn't have to be Gaussian. The uncentered transformation also gives us slightly better accuracy in estimating the covariance than the linearization approach we discussed earlier. Having gone through linearization and the uncentered transformation as examples of deterministic approximate inference, let's now have a look at stochastic approximate inference. The main idea really is to sample trajectories. To generate a trajectory sample, we first draw a sample from the initial distribution, and then iteratively we draw a sample from the distribution of the next state given the sample at the current state. On the right-hand side, we see some example of these kind of trajectory samples that we can generate using this procedure. The good thing is that we no longer have a parametric restriction to a specific kind of distribution. Remembering back to linearization and the uncentered transformation, we always approximated the predictive distribution by a Gaussian. This restriction is no longer there, and we can now describe multimodal distributions. However, our distributions are represented by these trajectory samples. And if we have to store all of them, for example, if we want to inspect the trajectory distribution more closely, we can run into some memory issues. Stochastic approximate inference is also used in sequential Monte Carlo methods, such as the particle filter. Now let's compare these two approaches. In deterministic approximate inference, we represent distributions using parametric forms, for example Gaussians, whereas in the stochastic case, we represent them using particles. This has some implications. The deterministic approach introduces bias, does not properly model correlation between time steps, but it's fast, does not require too much memory, and gradients of the expected loss with respect to some parameters are deterministic. In the stochastic case, we have no bias and account for time correlation through this way of ancestral sampling we discussed. While sampling can be slow, it is easy to parallelize. Because of the inherent randomness, we don't get closed-form gradients, but only stochastic gradients. Now that we discussed some ways to do long-term predictions in time series model, let's look at long-term predictions where the transition function itself is learned and described by a Gaussian process. We have the same Markovian state evolution as before, but now the transition function is described by a Gaussian process. A Gaussian process implements a distribution over functions. That means instead of learning point estimates of model parameters, which we get when we do least squares or regularized least squares, we maintain a distribution over model parameters. We can think of a Gaussian process as a generalization of a Bayesian linear regression model where the model parameters themselves remain uncertain. Therefore, we now have to account for this model uncertainty as well when we make predictions. We'll be looking again at two different approaches for making long-term predictions. Deterministic approximate inference, where we iteratively determine the marginal distributions of future states, and stochastic approximate inference, where we obtain trajectory samples. Now let's start again with deterministic approximate inference. When we compute the next state distribution, we need to compute the integral of the next state distribution conditioned on the current state, and we integrate out the current state with respect to p of xt. So this integral is exactly the same integral that we already looked at before. The additional complexity now with a Bayesian model, such as the Gaussian process, is that the conditional distribution itself requires solving an integral. I'm writing p of f here to indicate the distribution over functions. If you're more familiar with Bayesian linear regression, replace f with the model parameters theta and the equations will be identical. We can apply the same ideas that we could do in the case of deterministic transition functions. We can linearize the Gaussian process, we can use the uncentered transformation to push sigma points through the Gaussian process, or we can use moment matching where we compute the mean and covariance of the predictive distribution in closed form. Let's have a brief look at moment matching. Just to recap, our idea is to iteratively compute the distributions p of x1, p of x2 up to p of x capital T of future states. At every time step, we'll make a Gaussian approximation. This means starting from an initial distribution p of x0, we iteratively compute Gaussian approximations p of x1 to p of x capital T. Now, let's take one time step out and see what this looks like and what kind of problems we need to solve. Here on the right, I'm showing the Gaussian distribution of the state at time step t and the Gaussian process model for the transition function. To get the distribution of the next state, we need to compute this double integral where we integrate out not only the uncertain state, but also the uncertain transition function. If we do this, we get this red distribution here. Unfortunately, we cannot do this computation in closed form, but we can compute the mean and the covariance of the predictive distribution in closed form and then approximate the predictive distribution by a Gaussian that has the right mean and the right covariance. That approximation looks like this. The red distribution is approximated by this blue Gaussian, and now we can push this Gaussian again back through the Gaussian process, do the same kind of approximation, and get the distribution of the state at time t+2. This approximation, where we compute the mean and covariance of the predictive distribution in closed form, is called moment matching. And the key computation challenge here with the Gaussian process is to be able to compute kernel expectations. For some nice kernels, such as the squared exponential or polynomial kernels, moment matching can be done analytically. Let's have a look at an example in model-based reinforcement learning, where we use Gaussian process moment matching for long-term predictions. Here we learn the dynamics of a physical system using a Gaussian process. The state at time t+1 is a function of the state at time t and a control signal ut. The control signal itself is computed by a policy π that is parameterized by theta. For example, in this cart pole system down here, the state is four-dimensional, the position and the velocity of the cart, and the angle and the angular velocity of the pendulum, and the policy could be a neural network. We're interested in finding policy parameters that minimize an expected long-term cost, which is the sum of expected costs at each time step. For example, this cost function could be the squared Euclidean distance between the tip of the pendulum and the target position, which is indicated here by the red cross. We use Gaussian process moment matching for long-term predictions, which allows us also to get an estimate of the expected long-term cost. Because this approximate inference is deterministic, we can also get the gradients of the expected long-term cost with respect to the policy parameters in closed form and use a quasi-Newton method to find optimal policy parameters. Let's have a look at how this works in practice. So here we have the cart pole system. The cart is running on a track. We can push the cart to the left and to the right. Initially, the pendulum is hanging down, and the idea is to find a control strategy that can pushes the cart from left to right and then swings the pendulum up so that it balances in the inverted position in the middle of the track. So we are interested in learning to control the system from scratch. So to kick off learning, we apply random actions initially to collect some small data sets. So each of these trials is 2.5 seconds long, and we collect data at 10 Hertz. That means we get 10 data points per second. So now we collected 50 data points. We train our Gaussian process for the dynamics model and use Gaussian process moment matching for long-term predictions. And then based on that, we optimize our policy parameters. So now we are ready to apply the policy to the cart pole system. When we apply the policy, we see that the cart now stays more or less closely in the middle of the track, but it does not solve the problem of the cart pole swing up. The reason for this is that if you inspect the predictive variances a bit more closely, you'll see that the variances explode after 2 or 3 time steps. That means the system is very uncertain about what's going on. But now it has more data in this region of the state space where it's very uncertain. It updates the dynamics model, it updates the long-term predictions, and it relearns the policy. And so the next time it tries something, it looks like this. So it gets the pendulum up, or the idea of the upswing movement it gets, but it overshoots dramatically. So the reason for that is that it never had observations in that part of the state space, and again the uncertainties are very high. But again, it uses the new data to update the dynamics model and to relearn the policy. And then the next time it tries, you can see it automatically learns to slow down the swing up movement. That means it learned to improve just by itself. And over the next couple of trials, when it always takes more information into account, we can see a significant improvement compared to the previous trial. So here it almost got the idea, and then the next time it will get it. So this is actually one of the very few reinforcement learning algorithms that can learn from scratch, and you can see an improvement after every single iteration. And after 6 or 7 trials, it gets the idea, it balances in the middle of the track, and it's even robust to small annoyances or outside disturbances. So this approach is fairly general and it has been applied to a wide range of different robotic systems. For example, a cheap robot arm that uses visual feedback to learn to stack a tower of blocks, a tendon-driven robot arm that learns to hit table tennis balls, a robot arm that learns curling, a mobile platform that navigates through a maze, and a unicycle that learns to balance. It has even been applied to controlling throttle valves in combustion engines. This was a brief excursion into deterministic approximate inference. Now let's also have a look at what we can do with stochastic approximate inference. Here we are interested in sampling trajectories from a Gaussian process. We can also think of this as drawing functions from a GP. Let's have a look at this illustration on the right. We have some training data shown by the black squares. We train a Gaussian process using that data. The posterior mean is the blue line, and the posterior uncertainty is represented by the shaded area. If we draw sampled functions from this posterior Gaussian process, we expect the function values to stay roughly within this uncertainty region. So let's have a look. The functions we sample from the GP do mostly stay within the shaded area. They mostly agree in regions with the training data, but they have much more flexibility and disagreement in areas without training data. In order to generate functions from a Gaussian process, we would need to sample from a t-dimensional multivariate Gaussian, where t is the number of query points, that is, the points at which we want to evaluate the function. For example, here on the right, I evaluate the function draws at 500 points. That means we would need to sample from a 500-dimensional Gaussian. If we sample from this multivariate Gaussian, then sampling from a Gaussian process scales cubically in the number of these query points. So that's a problem. There are some ways to speed this up, for example in low dimensions or when we make structural assumptions. But let's also have a look at a different approach. Decoupled sampling. The key idea behind decoupled sampling is that we can exploit Matheron's rule to sample functions from a Gaussian process. With Matheron's rule, we can write a posterior distribution as a sum of two terms, a prior and a data-dependent update term. Matheron's rule allows us to think about the posterior in terms of samples and not necessarily in terms of a conditional distribution. It basically enables us to get a sample from the posterior using this two-step procedure. First, we sample from the prior. Second, we correct the sample by looking at the data and adding a data-dependent update term. What we have is a valid sample from the posterior. Here the only source of randomness comes from the prior. The data-dependent update term is a deterministic function evaluation. That's maybe similar in spirit to a GAN, where we sample a latent variable and then push it through a neural network to get a data sample. Here's an illustration of this procedure. First, we sample from the prior. In this figure, the sample is the orange line, observed data are these black dots, and the residuals or the error between the line and the data is indicated by this dashed line. Clearly, the prior sample doesn't care at all about the data, so we need to do something about it. In the second step, we figure out how the prior needs to be corrected in order to take the data into account. In this update term here, we see that we look at the residual between the observed data y and the prior evaluated at the corresponding inputs. That means we're looking at these dashed lines in these figures. If we add this correction term to the prior sample, we get a valid sample from the posterior Gaussian process. The sample is shown here by the blue function, and the posterior GP's mean is the dashed line and its posterior uncertainty is represented by the blue shaded areas. We see that the sample we just computed passes through the observations and it makes sense given this posterior Gaussian process. As we just discussed, the update term depends on the residual between the prior and the observed data. We can think of this update term to be an explicit mapping between the prior and the posterior. The decoupled formulation up here allows us to use different representations and approximations for the prior and the update term. Ideally, we can find approximations that can be evaluated efficiently so that we can get away from the cubic sampling complexity. For example, we could use random Fourier features to approximate the prior and a finite basis function representation for the update. If we do this, sampling from the RFF prior, which we can think of as a Bayesian linear regression model, scales linearly in the number of test points, and the update term can also be evaluated linearly in the number of test points. That means then overall that we can sample functions efficiently. That means sampling scales linearly in the number of test points. The decoupled sampling allows us to efficiently sample functions from Gaussian process posteriors. That means this approach is useful in applications that use function samples a lot. And here are some of these applications. For example, when working with deep Gaussian processes, then we usually rely on sampling for training and inference. Here's an example of a deep convolutional Gaussian process autoencoder applied to the MNIST dataset. Another application is Bayesian optimization, where we use Thompson sampling as an acquisition function. Thompson sampling directly requires sampling from a Gaussian process, so decoupled sampling is also useful here. We can also use decoupled sampling for drawing functions from GPs on Riemannian manifolds. And another interesting application we could think about is model-based reinforcement learning, where we use the sample trajectories to compute expected long-term rewards. To summarize, a key challenge we discussed in this video was how to do long-term predictions in nonlinear time series models. This requires propagating uncertainty. We looked at deterministic inference, including linearization and the uncentered transformation, which iteratively approximate the distribution of the next state by a Gaussian. We also looked at stochastic inference, which generates sample trajectories that we can use to compute the expected utilities. And in the last part, we discussed some of these approaches in the context of dynamical systems, where the transition function is modeled by a Gaussian process.